All right, we can call this series the white shirt series. Notice looking at the all the posted videos that I have a different colored shirt on every time I film this. I guess it's not surprising. I kind of do these in batches. But what we're going to tackle next is the topic of tolerances of orientation. We've sort of done tolerances of form. Tolerances of form is a simple but a very fundamental control that probably doesn't get used as much as it should, but in order to for some of the other controls to work, you almost have to have some sort of form control. So I encourage you to read through that chapter. It's fairly short. I know it doesn't read real easily, but spend a little time with the illustrations. Make sure that you get this idea that we are drawing a boundary around a perfect form. In other words, if we draw a surface as a flat plane, it will be drawn as a flat plane. And from that perfect representation, we project boundaries within which the actual feature has to fit. And that's not, the hardest concept to imagine. What is hard sometimes is actually establishing those and making sure that your feature falls within it. So that's more the realm of metrology or quality assurance. We won't get into the hows of any of this, but at some level you do have to be mindful of it. When we get a little further into GD&T, you're going to see that you're going to be given controls that are extremely powerful. They can put a lot of requirements on a lot of area, and they look simple, but to actually do them can be very difficult, very expensive. So again, that's geared a little bit more towards the engineer who's going to put the requirement on. I just want you to be aware of it, that every representation of GD&T you see on a drawing, one, it's not always right. In fact, in my experience, 75% of the GD&T that I see on drawings is poorly thought through or just doesn't make any sense at all. It's an unfortunate fact, but a lot of people who do put the information on the drawing really don't understand the system very well. So you'll always have that to deal with. But hopefully when you graduate from here online, you'll have at least enough understanding to recognize GD&T when it's done right or when it's done wrong. Okay, so tolerances of form, we saw the concepts of line elements and derived median elements. We saw the effects of material condition modifiers and how they can adjust the tolerance zone based on the actual size of a feature. I don't think I mentioned it in the previous video, but you'll often hear that material condition modifier called bonus tolerance. And I don't really care for that term, but in a sense it sort of is. And what it means is that if you have a material condition modifier and you have good control of the size of a feature, in other words, if you're turning a shaft and let's say you have 10 thousandths tolerance on the diameter of that shaft, and you can consistently put it within a couple thousandths, anywhere within that range, you can take advantage of that. You can say that, well, I've got a straightness tolerance here that's fairly tight, but for some reason when I heat treat these things, they bend a little bit. What would you do? You would take advantage of that. You would turn the shafts down closer to least material condition, and that would give you that additional straightness tolerance. So that's that idea of a bonus. And again, just like the application of GD&T, a lot of people misinterpret that. That doesn't mean you get that additional tolerance all the time. The only time you get it is when the feature is not at maximum material condition. Otherwise, at maximum material condition, you get what's listed there. Whatever that tolerance is, that's what you get and no more. But you can play the game. You can take a little bit of material off and gain a little bit of additional tolerance. Okay, so we'll call it quits here for tolerances of form unless you have any questions. Again, I want to make sure that if you do have any questions, you text me, call me, email me. Text and email probably is the very best, but I will be glad to do a separate video. I will call you. We'll have a conference call, whatever it takes to make sure that everybody's getting what are at this point fundamental concepts that you just have to grasp the idea of the tolerance zone, the material condition modifiers, and how they're used and how they're presented in the feature control frame. Because it only gets more complex from there. All right, so the next topic and the next level of complexity is tolerances of orientation. Now, I suggested to you that tolerances of orientation were sort of the flip side to tolerances of form, and they are, but only in the sense that a tolerance of orientation always requires an evaluation of that feature with regard to something else. We are always comparing where something is or how it's oriented to some other feature. In order to do that, in order to deal with things that aren't intrinsic, like all the form controls, we have to introduce another concept, and this is a concept that is unique to GD&T. It is, again, somewhat poorly understood, I think, by some engineers, of what its purpose is and how to represent this concept. And the concept is the concept of a datum. When I said that an orientation control is going to establish a tolerance zone of orientation, it is always going to be comparing that feature and its orientation to some other feature. The other feature then has to be considered a datum. What is a datum? A datum is a reference point. It's something that you use to measure from or measure in comparison to, and that's really all it is. Beyond that, we have a separate set of symbology that you have to be exposed to. You're going to see that symbology on the drawing, and you're also going to see it represented in the feature control frame. And on top of that, we actually have two different types of datums and two different types of datum symbols. So what I'm going to do in this video, before we even talk about tolerances of orientation, is we're going to talk about datums, how they're represented on the drawing, and what the distinction is between these two different types. After that, then we'll jump right into tolerances of orientation. We'll see that the datums are applied in the feature control frame in all instances. In fact, that's one of the telltales of a proper GD&T callout for an orientation control, is it must have a datum in the feature control frame. If it does not, something's wrong. You can't really interpret it. And then again, if we didn't have enough complications, datums can be evaluated for their material condition. Just like the feature that we're controlling, the datum which is a feature that we're comparing to, also has a material condition. It could be large or small or somewhere in between. So we can actually use a material condition modifier in evaluating the tolerance zone of the feature and the datum itself. And again, that's a complication. It's got to be done right. You don't just do it because you feel like you want to do it. It is something that has to be looked at very carefully, because it can add a lot of tolerance to the tolerance zone, and you can end up with some pretty unfortunate characteristics if you're not careful. So let's start out and get a grasp of the symbology. Now what I'm going to do, I will have, by the time you see this video, I will have posted a scan of section 3 symbology in here. Now you've seen portions of that, you've seen the tables for the GD&T symbols, some of the other symbols, material condition modifiers, symbols that you've already seen, the references, that sort of thing. But we're going to evaluate the datum symbols, the two different types that are available to you. Now, over the years, the datum symbol and the way it's been applied has changed a little bit from one standard to the next. So what you're seeing, or what I'm going to cover, is the current way it is done. It was done in a number of different ways over the years, so if you have an old drawing, it may not exactly conform to this, but pretty consistently now on newer drawings, especially on CAD drawings, you're going to see the datum symbol applied as I'm going to explain it here. Okay, so the datum symbol is deceptively simple. It is a rectangular box. And in that box, just like the feature control frame, one thing goes in there, and that is the datum identifier. The datum identifier will always be a letter. In the instance of this first datum symbol, in this box you will see a letter. It will be A through Z, and as I recall, you don't use O or I or Q. There might be another one in there that they don't use, that is just to prevent confusion between numbers and letters. So it pretty consistently in revisions and in datum callouts, we don't use those letters. Okay, so you've got A through Z, that's 26, minus those 3. You have 23 datum notations available to you. What if you need 24? Well, if you need 24, you're working on something incredibly complex, and you're probably overdoing it. I have worked on some very complex machinery and equipment for aircraft where a single drawing might have 20 pages to it. I don't think I've ever seen them do what they're suggesting here in the standard that you can do, but you can do it, so that if you need that 26th or 24th symbol, you double the letters. A, B, A, C, so on and so forth. So you basically have an unlimited or a very large number of datums available to you. Again, very seldom are you going to see anything close to even 23 datums on a drawing, but if you do, you might see that double datum notation. Okay, so once we picked our letter and it's in the box, we have to apply it. We have to point the symbol to the surface or the feature that we're interested in. There's a million different ways to do that. If you look at figure 3.3 in the handout, you'll see that you can stick it on the surface, you can stick it on an extension line, you can attach it to a chain line, you can attach it to a feature control frame. Lots of ways to do it. I will let you look at those. I'm not really going to hold you responsible for it because it's pretty obvious that it's a datum and what the actual datum is. Now there are a couple little subtleties in there as to whether you're talking about the surface of a feature or the derived median element of the feature. Don't worry about it. Push comes to shove, you can look it up in the handbook. I'm not going to give you all the whys and wherefores for that. I just want you to be able to recognize this symbol and of course the special little special little sticker foot or whatever that is, that you use to attach or make clear what is actually the datum feature surface. This whole triangle thing is a new thing in the last few revisions of the standard. Many drawings, older drawings, you won't see this. You have the option of having a completely filled in triangle or a unfilled triangle. There is no distinction between them. One doesn't mean anything that the other one doesn't mean. I would say in all cases, if they're going to do one or the other on a drawing, you'll see it very consistently. You'll never see them mixed like that. I don't know why they even make the distinction. It may have been because of limitations of CAD systems or something. I don't know, but that style, either filled or unfilled, is completely optional, and it means nothing. It still is simply a attachment point for the datum. Okay, so what is a datum? And what kind of datum is this? Well, let's make that distinction here. Fortunately, unlike some of the very important distinctions in GD&T, this one's going to be extremely clear. You're going to know whether you're dealing with one datum type or the other. The two datum types are datum features. Okay, datum features are going to be in this rectangular box. The other type is fairly rare. It's used in special instances. I'll give you an example of that later on when we talk about position. There's a real good example in the standard about when we use them and how we use them. But I'll just draw one up here so you can see what it looks like. It will look like a circle with a line in it. That is obviously the first visual clue that you're not dealing with a datum feature. You're dealing with a datum target. Okay, the difference between the datum feature and the datum target is this. Datum features are used when you have a feature that is going to be the datum. Seems obvious, but what does that mean? That means that you have a part, and let's say you have a milled surface, and you want to consider that your primary datum. You're going to start measuring from that milled surface. That's an obvious datum. It's an actual feature. It's machined, and that feature will always be there no matter how much more processing the part's going to get. An example of a slot or a tapped hole or a groove or an edge, a diameter, all of those things that are good, precise features machined for a purpose, and they actually exist on the part and will exist throughout the lifetime of the part, or the lifetime of the processing of the part. That is a datum feature. Now, what's a datum target then? A datum target is that thing that isn't like that. There are components that don't have a lot of features on them. If you think about, I don't know, well, I'll use the example from the book. The book shows like a car hood. Okay, a car hood is curved, you know, in all different directions. Doesn't have a lot of holes in it. It doesn't have a lot of slots or flat surfaces. It's a weirdly shaped, hard to measure from component. But still in all, you've got to measure it to make sure that it's going to fit on the assembly at the assembly plant. So we have a technique using a datum target where we can temporarily identify locations by measurement. Usually that we are going to set up on those points and take measurements from. That's well and good when the part is sitting up on a jig or a fixture with those points on that fixture. Once you take that component off that fixture though, those points aren't there anymore. You couldn't look at that part and say, oh yes, well I measured from here, here, and here, because those features cease to exist. They never really did exist. We were just sort of picking specific points on a part to measure from. And again, I won't talk about this one too much. The reason it is like this is that we have to often provide information in the datum target that we don't have to with the datum feature. The datum feature just needs a letter. The datum target also always has a letter in it, but very often, I would say in most instances, it's also going to have a number. So it would be like A1, A2, A3, because very often we have to establish a number of datum target points. I'll give you an example here. If I wanted to say, put this eraser on a fixture and I wanted it to sit level, I would establish 3 datum points on that fixture, and I would set that eraser on it, and it would sit stable and level and all of that. When I pull the eraser off, there's no indication that I measured from or leveled the part on this surface or where. And that's the difference between a datum and a datum target, and that's why I need like 3 datum target points here. So on a drawing I would show those datum targets, and I would provide measurements where those specific points are on the part, and we design a fixture to hold those parts. The upper area is often empty, but there are instances where we have to specify what the nature of the contact is on that datum target. In the case of my 3 fingertip points, I'm touching on 3 geometric points. But I may have to identify in the design of the fixture, I may have to identify that I want a 1-inch diameter spherical radius tooling ball or something like that, or I want a contact area that is a 1/2 inch in diameter. I can specify the nature of the contact point and how many there are in this upper area. Again, that's very specialized. It's more into the tool design realm. So just recognize the datum feature, recognize the datum target, recognize that datum features are actual features that are part of the component and have some function to do with that component. Now there are instances where, as we're processing a part, we might actually drill a hole, let's say an extra hole as a datum location, and then in subsequent processing we may cut that hole out, or we may drill it out and tap it. Some instances where datum features are used and then modified properly, we should identify them as datum targets. In other words, the datum should remain on the part throughout its processing. Okay, again, I'd like you to read through this. You'll be able to read about how the datum targets work, and some of the subtleties of application of the symbology. There's really not much more to datums than that. As we go along, I'll show you how you use material condition modifiers with datums, how we are going to use datums to establish sort of a perfect geometry we call a datum reference frame, so that we can position and orient and fix in space a component so that we can evaluate all the features on that component relative to a fixed location. And that is sort of the job of the fixture designer or jig designer. He has to say, well, I've got a raw casting here and I have to put it and hold it in place so that you can put it on a milling machine and mill surfaces and put holes where they're supposed to be. So in other words, that fixture has to orient and align the part relative to where the machine thinks it is, and put those parts or put those features in that part. The the art of doing that, of course, is again a separate side of GD&T that we won't cover. But be mindful that whole datum system is meant to deal with what we talked about before, which is constraints and the degrees of freedom that a part has. If I go back to my eraser example here and say I want to fixture this thing for machining, and I say I'm going to create a fixture that has 3 geometric points that this can sit on, I can look at that and say, now I have constrained this thing in space. I don't have all the degrees of freedom that I originally did. So let's look at that. Without any datum reference, this component can be considered to be free in space. It can move this way, it can move this way, it can move this way, it can rotate this way as a yaw, a pitch, or a roll. Obviously, we don't want that doing that while it's on the machine, so we have to constrain it. My fixture initially then is going to constrain it, and now we have to look at what is constrained. What can't this thing do? Well, if my rule is that this component and this surface have to touch these 3 points, I have prevented it from doing this. Certainly it can't lift off the 3 points and still meet my requirements. It can't roll, otherwise it'll come off of that point. So I've constrained those degrees of freedom. Let's look at them in the groups that we put them in. We put them in translation groups and rotation groups. So what constraints do I have on translation? I can still do this, so I have that degree of freedom. I can still do this, and I still have that degree of freedom. So I still have 2 translational degrees of freedom. And what I want you to think about here is, why can I do this? Well, I can stay in contact with these 3 points and still slide around. I can still stay in contact with these 3 points and still slide around. Obviously, I can no longer translate in this, let's call it the z-axis, because I have to lift off those points. So I've constrained 1 translational degree of freedom. Let's look at the rotations. I can't do this, I can't pitch, I can't roll, but I can yaw. So I've still got that degree of freedom. What if I really want to lock this thing down in 3D space? I have to start adding additional datums. I have these 3 datums. Let's say I want to tackle the translational degrees of freedom that I still have left, the fore and aft, side to side. I can add additional contact points or additional datums. Let's say I force 2 points here and say this part must now sit on these 3 points and it must bump up against these 2 points. At that point I have constrained this translational degree of freedom, but not this one. I can still translate this way and stay in contact with those 3 points and these 2 points. So, in order to completely lock this thing down against translation, I add another point here. I have 3 points, 2 points, and 1 point. 6 points constrain those 3 translational degrees of freedom. What about the rotational degrees of freedom? If I go to these 2 points, I can no longer yaw. I couldn't pitch in the first place, I couldn't roll, so I have constrained